A queue is one of the most intuitive data structures. The first element to arrive is the first to leave, establishing a strict sense of order from the moment elements enter the structure. This behavior is captured by the principle of first in, first out, or FIFO. Once an element is added, it must wait behind all others before it can be removed, ensuring that processing always follows the exact sequence of arrival. Given the first-in, first-out structure of a queue, an array seems like a natural choice for implementation. It provides fixed, contiguous storage, constant time indexing, and a straightforward mechanism for tracking positions using front and rear pointers. When an element is enqueued, it is placed at the index indicated by rear, which is then incremented to the next available slot. Conversely, when an element is dequeued, it is removed from the index indicated by front. Because front must always reference the first element in the queue, the remaining elements are shifted one position forward to preserve this ordering, after which front continues to point to the starting index of the array. For small systems, this design feels efficient, predictable, and clean. However, a closer examination reveals a subtle but significant limitation that is not immediately apparent. This limitation becomes evident when we analyze what occurs during a dequeue operation. In a naive array implementation, where the queue is expected to occupy the first n positions, each removal triggers a cascade of shifts. When an element is dequeued from the front, all remaining elements must move one position forward to maintain contiguity, effectively closing the gap left behind. This seemingly innocuous step carries a steep performance cost. Shifting n elements requires iterating through each one, resulting in linear time complexity, O of n, for a single dequeue operation. One possible response to this inefficiency is to avoid shifting the elements altogether. Instead of moving every remaining element forward after a dequeue operation, we could simply advance the front pointer and allow the queue to logically begin later in the array. In this approach, the array itself remains unchanged, only the boundaries of the queue shift. The front pointer moves forward to mark the new first element, while the rear pointer continues advancing as new elements are enqueued. This design simply changes the immediate O of n cost of shifting, restoring dequeue to a constant time operation it was always meant to be. However, this adjustment introduces a new problem. The array is still being treated as a linear structure with a fixed beginning and end. While the front pointer can march forward indefinitely, the rear pointer is confined by the array's physical limits. As rear continues to advance, it will eventually reach the last index, at which point no more elements can be added, even if earlier dequeue operations have left unused space at the front of the array. The key insight is to eliminate the notion of a true end. Instead of treating the array as a straight line, it can be interpreted as a loop. When the rear reaches the final index, it wraps around to the beginning and continues from index 0. The front advances independently as elements are removed, freeing positions that can later be reused by subsequent insertions. This design allows the queue to fully utilize the array's capacity, without shifting elements and without wasting space. The array becomes a circular buffer, a self-contained loop where memory is continuously reused, allowing the queue to operate indefinitely within a fixed allocation. This behavior is enabled by the modulo operation. For any integer k, the value of k mod n always lies in the range of 0 to n minus 1. In other words, no matter how large k becomes, taking it modulo n maps it back into a fixed set of n possible values. In the context of the circular queue, n corresponds to the size of the array, which in code is represented by max size. Thus, the mathematical expression k mod n becomes k mod max size in C. Because max size is the capacity of the array, this ensures that every updated index remains within the valid range of 0 to max size minus 1. As a result, when an index advances beyond the last position, it does not move out of bounds. Instead, it is mapped back to the beginning of the array. What would normally be a linear progression of indices becomes a circular one. Using this design, no elements are physically moved. The system creates the illusion of movement purely through index manipulation. InQ and DQ operations now take constant time, O of 1, because they no longer depend on shifting data or the size of the queue. The array is reused efficiently, cycling through available space as operations occur. By removing the notion of a fixed beginning and end, the queue becomes both space-efficient and time-efficient, operating predictably within a fixed block of memory.